Yeah, it is pretty great.
Switch.
Yep.
All right. So just to let everyone know that the recording has started for the online session. I'll just give it a few more seconds just to let people who come in, and then we will begin shortly with our first. So while people are joining in, like I said, we're going to go through all the talks first and then the Q&A at the end. For the Q&A part, feel free to unmute yourself and ask questions. Or if you prefer, you can just type in your question in the chat and I can read it out on your behalf. And if you do so, if you do write your question on the chat, I kindly ask you to just prefix the name of the speaker or the person that you want to direct your question at so that we know like who they're going to. And without further ado, let's get started with another exciting session at ICSE 2022 with program analysis, my favorite subject. And this is session number 5. The first talk that we have for you today is from the journal first track. And we have Ryan here presenting to us guided feature identification and removal of resource constraint firmware. Ryan, the floor is yours.
Great, thank you so much. Now that I know I can and there we go. All right, so thanks for the introduction. I'm Ryan Williams from Northeastern University. I think I'm joined here by my authors, Talmay Ren and Lorenzo DiCarlo from WPI. And I'm just going to give a presentation on guided feature identification for resource constraint firmware. So as we know, protocol, like kind of any other program out there, you tend to get feature and things like that. And a lot of times these features are unnecessary to the overall functionality of the base program. So we actually found in some of our evaluation set that leftover code related to a feature that was removed at build time accounted for up to 29% of the overall lines of code in the compiled binary. So all these features that we have here can end up resulting in a lot of dead code. Disable them. QTT, for instance, is a pretty straightforward pub sub of a bunch of something here like sensors, like temperature sensors, which would be the client publish information on a given topic. Like here, they're publishing their temperature on the topic temp to the monolithic MQTT. And then we can have any data consumers or subscribers, which would be like here that can listen to the temperature topic and it gets the readings from those individual sensors. So in a case like this, MQTT, as we saw in the previous slide, one of the implementations has roughly 19 optional features that can be build time. And as we can imagine, if we're doing something pretty simple, or deployment, we may not need like WebSocket to TLS or the features that would just pertain to a web instance. So we've designed Pratt in order to facilitate the identification of these features and removal of their actual code artifacts so that we can reduce the amount of code that could be left over in the compiled binary. So the first step of Pratt is this analysis stage where we take the native build system like make or CMake or autoconf, and we infer the features from those build files, like the make file. And once we have a given feature, we run the compilation with it toggled on, and then we run compilation with it toggled off. So we have two separately compiled binaries. And then we run all the given unit tests and tests that come bundled with it. And because the binaries were instrumented gather code coverage, we then can just take the differential of those two binaries and we see code highlighted. So we posit that the code that is executed in one of those binaries, the one that pertains to the feature that we've been toggling. So once we gather all that, feature selection stage, which is the one step that in the loop. So we give them a web interface that goes a GitHub-like diff kind of individual lines of code that would be removed for a given feature, what they are, and how many lines of code you'd be removing by disabling that feature. So the user selects those features and then passes it on to the next step, which is back to being automated, where look up all the mappings from the code block that you specified. It'll excise them, the respective source files, and then we that came bundled before saying this seems to be working is now ready. We looked at 3 primary questions. One was, can Pratt identify all the features within a code base? Does this approach actually lead to a measurable reduction in the amount of unused code? And then lastly, do the deep loaded programs retain correctness after that feature removal? So for number 1, we found that in all evaluation tests, we found all the true features with 1 false positive. This false positive was with one of the MQTT implementations, but that ended up pertaining just to a flag to build with or without a shared library, so it wasn't a breaking feature for this. As far as overall code reduction, we can see that the Pratt-based approach tends to lead to a non-insignificant amount of code reduction versus the native build system. And lastly, for correctness after feature removal, we rely on extensive testing, dynamic analysis-based approach. And when those tests aren't always available, we then use the CLI log execution environment to generate test cases. And for all our test cases that were generated with CLI or synthesized test cases, those resulted in code coverage on average. So we were pretty confident in saying we didn't introduce any new errors. Yeah, so that is Pratt. It's an approach for identifying and removing features in software. There's a couple limitations here where if the code base is very large, we may need to compile many times, and that could be non-trivial. And precision of code removal is obviously reliant on the coverage quality of. Okay, and with that, I'll say thank you. And if anyone has any specific questions, feel free to reach out to me directly or see our full-length talk and paper on the ICSE site. Thanks.
Thanks a lot, Ryan. Yeah, so like I said, the questions are going to be in the Q&A session at the end of all the talks. But if you have the questions, keep them coming on the chat if you want. Or at the time of the Q&A, you can unmute yourself and ask the questions directly to the speaker. So thanks again, Ryan. And now we're switching gears to another track from ICSE, Software Engineering in Practice. And Pavle is going to present to us today a static analysis framework for data science notebooks.
All right, thank you, Karim. So my name is Pavle Subotic. I'll be presenting a static analysis framework for data science notebooks. I'm from Microsoft Azure Data Labs, and this is joint work with my colleagues Lazar Milikic and Milan Stojic. Okay, so notebooks have become the de facto coding environment for data scientists, and you can see that the growth has been immense. In only a few years, it's grown almost exponentially. And currently, there's over 10 million notebooks just on GitHub. And all the big companies are throwing the hat in the ring. And most importantly, the semantics of notebooks are here to stay. On the other hand, they're quite notorious for having coding issues. So there's been plenty of studies showing the bad code in them. And as the saying goes, where there's smoke, there's fire. Where there's sort of code smells, it's likely that there's a lot of semantic bugs here. And so the natural question is, can we bring static analysis to notebooks? So for those of you who don't know, notebooks, they're just programs, but they're divided into cells, and you can execute each cell in any given order, and you can add and remove cells. So given a change to a cell, and say we execute, say cell 1, we may want to know what the consequences are if we execute other cells. And so, for example, in B, if you execute cell 2, 4, and 5, you'll get what's known as a data science data leakage, meaning that we've done some normalization to the data, and then we've split the sets into training and testing, and then we've actually done the fitting, and that will give you very good results, but they won't be actually like that in the real world. And the other example shows that if you execute change cell 1 and execute it, and you directly execute cell 4, omitting to execute cell 2 or 3, you'll actually get the wrong result coming from the old state because X hasn't been refreshed with the new value. And that's a big problem with notebooks. So how do we do this? So the challenge is that we don't have the standard semantics anymore. So you can execute this notebook in this order, 3, 4, 5. You can execute it 1, 4, 5. You can execute it 1, 2, 4, 5. So what we've done, we've taken the abstract interpretation framework and we've added this notion of this phi predicate. And this tells you whether you can propagate the abstract state to another cell or not. And so the way the static analysis works, you do a intra-cell analysis, which is standard, abstract interpretation, and then depending on the phi, you can decide which other cells in the entire notebook you should propagate to. And you keep doing this until you terminate. So you can terminate by having a cell that has phi false on all its outcoming edges, or if you reach inter cell or a notebook subsumption or fixed point. So this can look bad. It can look like it's exponential, but in reality, the phi success rate is quite small. And that's because typically there's no dependency between every cell in a notebook. And K is often not deep, so small, because we typically reach a point where it cannot execute anymore because phi is false, or because we reach a fixed point. And so in this use case, we wanted to keep the analysis quick, so not to disrupt the users. And we can see that for the two analyses, they largely stay under a second, with some cases that take a few seconds. And you can see the result is what I said before, that phi is typically about 10%. And you can see as K increases, so the depth increases, the number of subsumptions increase, and the actual execution time doesn't improve much anyway. So we have many use cases in mind, and we're now looking to develop this more and hopefully open source this at the end of the year. Thank you very much.
Thank you, Pavle. Again, any questions, keep them until the Q&A session or write them down in the chat and we'll get to them during the Q&A session. And now switching gears again, yet one more time. Yes, the next talk that we have Pei-Ming from the technical track, Pei-Ming is going to talk about POS or PUS, a fast and highly efficient solver for inclusion-based pointer analysis. We're ready whenever you are.
Thank you for the introduction. Yeah, I'm ready. My name is Pei-Ming from Texas A&M, and thank you all for attending. Today I will introduce my work on partiality solver, which is a faster solving algorithm for inclusion-based point analysis. So just a quick for those who may not be familiar with the topic. Point analysis is a fundamental program analysis technique that backs a lot of different kinds of static analyzers. On one hand, if you want a precise point analysis, because it can lead to much less false positives. But on the other hand, a precise point analysis is also hard to scale. So at a high level, point analysis computes a set of objects that could be pointed by pointer or references during runtime. And it helps to analyze program language with pointers or references. And it's also helped to resolve indirect function calls, such as function pointers in C and virtual functions in C and C++ and Java to build a And as its name suggests, inclusion-based point analysis computes the point to information by abstracting different statements into inclusive functions, as shown in this table. And then the problem can be abstracted into a function graph with each node representing a pointer and each edge representing an inclusive functions. The result is then computed by finding the minimal fixed point such that all the constraints are satisfied. So there are currently two widely used solving algorithms for point analysis. They are namely wave and depropagation. So at a high level, wave propagation will topologically sort the entire graph and then propagate the point to information in topological order and repeat it until reaching a fixed point. And the deep propagation, on the other hand, will propagate the point to information in a depth first manner. So both algorithms have to take the graph, the wave propagation will have to re-topologically sort the entire graph. So, but what we observe is that at each iteration, when you add in new edges and which change the topology of the graph, only a small subset of the graph are affected by the update and need to resort again. So the point information need only to be done on this effective subgraph in topological order. So take this as an example. When compared to the wave propagation, POS will only sort the nodes 2, 5, and 8 and propagate information in that order, while the wave propagation will have to re-topologically sort the entire graph. And when compared to the deep propagation, because deep propagation does not propagate point information, it will have to recompute the point to information from V1 to Vn twice, while POS only propagates information between these two nodes once. So we also formally prove the correctness of the algorithm. So if you are interested in the detail of the proof, please refer to our paper. And finally, we evaluate the POS on our set of benchmarks. The table shows that the effective subgraph will only contain about 3% of nodes and 2% of edges of the entire graph. Thus, only need to resort the that small graph instead of entire graph, and which means most of the redundant computation can be skipped. And for the performance, when we applying partial POS on to solve context-insensitive, field-sensitive, context-insensitive point analysis, is more than 3 times faster than wave propagation and 2 times faster than deep propagation on average. When applying to solve context-sensitive, field-sensitive point analysis, is more than 7 faster than wave propagation and almost 9 times faster than deep propagation. Yeah, and that's all my presentation. So thank you.
Thank you, Amy. All right. Our next talk is going to be Tao, who will speak about characterizing and chat mini programs.
Hello everyone, I'm Wang Tao from University of Chinese Academy of Sciences. It's my honor to be here and talk about our work characterizing and detecting bugs in WeChat mini programs. Sorry, maybe something wrong. Wait for a minute.
That's it.
Can you see my screen? Okay.
Yes.
Yes, we can. But now we can't.
Yeah, no more.
Sorry. Maybe I share this screen. WeChat is one of the most popular messenger and social media app. With WeChat, people can message their friends using text, photo. People can also share their favorite moments and enjoy some convenience features provided by, such as payment. WeChat is more than a messenger and social media app. It is a lifestyle for over across the world. WeChat mini programs are app-like platforms that exist within WeChat app itself. You do not need to download and install as Android and iOS app. And mini programs, people no longer need to install so many apps. When they want to use an app, they only need to find the corresponding mini programs in WeChat. Mini program development framework contains two layers, the random layer and the logic layer. The random layer is responsible for UI display, and the logic layer is responsible for program logic written in JavaScript. The two layers run on two independent threads, and they communicate with each other through an asynchronous and event-driven mechanism. WeChat app also provides for mini program development, such as location, Bluetooth, file access, and payment. However, bugs can occur during the development of many programs, such as JavaScript bugs, compatibility bugs, asynchronous bugs. For convenience, we call WeChat mini program bug as WeBug. To understand WeBugs, we conduct an empirical characterize WeBugs and try to investigate the root cause and the fix strategy of bugs. Based on the bug patterns we summarize from our empirical study, we propose a static analysis tool with detector and found 11 new bugs in 25 popular WeChat mini programs. We collect 83 WeBugs from 3 sources: GitHub, offshore developer, online WeChat mini programs. These bugs cover various stages of development. To understand WeBugs, we try to answer 2 research questions: the root cause and the fix strategies. We identify 6 types of root causes. The first is the differences in execution environment. Next is API misuse. Syntax errors can also happen in WeChat mini programs. Developers often assume that data shipped from external requests meet their expectations and forget to asynchronous errors can also happen due to the synchronous and event-driven mechanism. For bugs, we can divide them into the about 5 types. We group them into the logic errors. Some APIs in WeChat mini. For example, the API Weixin.compass change gets different return values on Android and iOS devices. The next case is the incomplete layout adaptation to anonymous screens. With the development of the mobile phones, more and more components are on the screen, such as camera, top notch, and the bottom bar. Rendering programs on the restrict areas can cause some inconvenience. Here, we can observe that the play button of the video is obscured by the camera. Therefore, developers need to adjust their style code according to the target device screens. We call this as the safe area. Developers should code based on the safe area. We found that the fix strategies of WeBugs are highly related to their root causes. We summarize 4 common fix patterns for almost half of WeBugs. Our empirical study has reviewed some common patterns, and we designed a static analysis tool to detect them. Among them, we summarize 3 common bugs. One is the incorrect invocation of platform-dependent APIs. Pattern 2 is the incomplete layout adaptation to anonymous screens, and the pattern 3 is the improper handling of return data in invoking asynchronous APIs. We detect 11 true bugs in 25 popular mini programs collected from GitHub, and 7 of them have been confirmed. The table shows the detailed detection result. In conclusion, we carry out the first empirical study on the bugs in mini programs. We collect 83 bugs from real-world mini programs and perform an in-depth empirical study on them. More details can be found in our paper and GitHub. Thanks for your listening.
All right. Thank you, Tao. Next talk we have, Akshay is going to talk about their work with Jens Felsberg about fast and precise application code analysis using a partial library.
Yes. Hi, good morning. I hope you can see my screen.
Yep.
So my name is Akshay, and the topic of our paper is fast and precise application code analysis using a partial library. So analysis time is still an issue in static analysis for cases like really large programs or a large collection of programs like an app store. And one way to achieve speed up is to do an application code analysis. So an application code analysis speeds things up by focusing the analysis on the application code. So if you see the program code split up here on the left, you'll see that the application code constitutes less than 1% of the Java bytecode in our NGR benchmarks, whereas the bulk of the program is the library, which includes the standard library and third-party libraries. However, if we take the naive approach of ignoring the library entirely, we miss too many errors. We get too low a recall. So we still need to model the library somehow. And to evaluate how an application code analysis is doing, we use the whole program analysis results as the ground truth. And we define two terms, precision and recall. So precision says out of the application code analysis errors, how many were true positives? And the recall definition says out of all the whole program analysis errors, how many did the application code analysis catch? So the current best application code analysis for Java is Avros. And here is an overly simplified view of how it works. So there are many details that I'm leaving out, but this should be enough for the discussion. So Avros over approximates the library into a really compact summary. And all the information from the library pointers is merged into a single summary pointer. So the result, if we take the whole program analysis as the ground truth, is that the speed up is really large because the library summary is very compact as compared to the whole library. And recall is theoretically 100% because Avros does an over approximation, but precision is only 59%. And let's look at what this means. So let's look at what users expect from precision. So user studies user studies on what developers expect from static analysis tools show that we should aim for 80% user perceived precision. But one issue is that whole program analyses themselves struggle to achieve this 80% user perceived precision. So what we need from an application code analysis is that it needs to get 100% precision relative to the whole program analysis. Otherwise, we are not going to meet the 80% user perceived precision. But the current best available is Avros, which only has a precision of 59%. And the reason why Avros is designed this way is it was designed as a recall-focused verification tool. But let's see what we can do to meet user expectations. So here is an overview of our solution to this problem. We introduce a new tool, QueryMax, which is a preprocessor to an existing static analysis tool. So given a specification of the application code, the library, and the analysis queries. So here the analysis queries, for example, for a cast check analysis could be all the downcast errors in all the downcast instructions in the application code. So given these three inputs, QueryMax selects a partial library that covers most of the client analysis queries, and library pointers outside the partial library are treated as the bottom element in the abstract domain. So this means that if we're running a null pointer analysis, we would treat everything outside the partial library as not null. So where the partial library is basically an under approximation for the library. And this partial library plus application code is fed to an existing static analysis tool that now gets errors which are 100% precision and 87% recall with a 10x speedup. So we've effectively traded a small amount of recall for a large speedup. And yeah, that's about it for this talk. Thank you for listening.
Thank you, Akshay. And last but not least, the last talk we have in the session is going to be Mike, who will talk about inference and test generation using program invariants in chemical reaction networks.
Awesome. Thank you. I'm Michael Gerton, and I'm presenting inference and test generation in program invariants in chemical reaction networks. Molecular programming is an emerging computing paradigm. It can implement technologies such as logical circuits, neural networks, or molecular robots. As these technologies become more complex, they can even implement intelligent drug delivery and other nanoscale technologies. When we want to implement these molecular programs, we can start with the functional behavior we want, which can then be implemented in a DNA solution, thus creating a physical output. However, we still need to know whether or not these programs' behaviors are correct, but it's often infeasible to test this in vitro, so we focus on the simulation layer of the program. The current state-of-the-art chem test requires us to have manually generated specifications in order to evaluate these programs. In order to represent molecular programs, we often use chemical reaction networks. Here is the parity function, which takes an input x and returns a value whether or not it is even or odd as a Boolean. And here's its implementation as a chemical reaction network. It consists of 4 reactions and 4 species, with x as the input species and PE and PO as the output species. If we wanted to write a specification for this parity function, we first want to think about the behavior we expect the function to represent. The first one I can think of is that if x is odd, we expect PO to be true. To write this as a specification, though, we can use techniques from linear temporal logic to go and express this that the property is true at all times after the point in the simulation we evaluate it. We can also write metamorphic specifications, such as this one here, which involves 2 simulations of the model. As these models become more complex, the specifications can also include things such as, shown here, probabilistic bounds that are checking properties in the model. Given an arbitrary CRN, even if the functional behavior of the model is relatively simple, generating a complete set that represents the full program's behavior can be both time-consuming and difficult, even for those who have experience with these programs. So we asked, is there a way to infer the specifications for these chemical reaction networks? Borrowing techniques from Petri nets, since there's been shown an equivalence between stochastic chemical reactions and a certain implementation of Petri nets, we were able to use linear invariants, or P-flows, to help infer some of these specifications from the models themselves. In this work, we present Chem Flow, an invariant inference technique that can be used for model comparison as well as test case generation. Chem Flow works by first generating invariants of 3 types. The flows are the simplest type, using simply species counts in order to be evaluated. The inequalities use additional information, such as the reaction counts, but uses the same evaluation, so they have a weaker oracle. And the irreducibles use both the species counts and the reaction counting, but requires additional scaffolding to be evaluated. These are the most costly to evaluate, but do add additional coverage compared to the other types. We can then use these invariants to do model comparison to go and compare these molecular programs and see if there's issues in the larger model. We can also use them to generate test suites that can be implemented in the current state-of-the-art chem test, which is used to evaluate chemical reaction networks for faultiness. In order to evaluate Chem Flow, we used 13 subjects, 9 of which we were able to generate manual specifications following the chem test approach, and 4 of which we were unable to generate the specifications, including natural models such as E. coli, which had nearly 400 species and reactions, respectively, or 500. When we looked at fault detection, we saw that in the 9 subjects that had manual specifications available, flows had a good fault detection in general, but when we added in all 3 types of invariants together, we saw fault detection on par with the manually generated chem test specifications, without the time and labor required to go and create the specifications themselves. We also saw similar performance in the 4 subjects without manually generated tests on the invariant tests. When we looked at model comparison, if we recall the E. coli organism mentioned before, when we generated the invariants for that model, we found that there were certain islands of behavior where species and reactions that should have interacted with the larger model as a whole were not. When we addressed this with developers, they pointed out this could be a sign of model quality issues, and they wanted us to continue to investigate these invariants on a larger set of natural programs in order to investigate some of their processes as well. Overall, in summary, we've presented Chem Flow, an invariant generation technique that can be used for fault detection in chemical reaction networks, as well as investigating model quality in natural programs. We do have artifacts available online, and I'll be happy to answer questions in the Q&A. Thank you.
Thanks, Mike. And thanks to all our speakers. Greatly appreciated. And now we can start our Q&A. We have about 26 minutes or 25 minutes or so for Q&A. So like I said, you can ask your question, just unmute yourself and ask, or if you want to post that on the chat. And I see already our first question on the chat from Akshay to Tao. So the question is, are WeChat bugs different from bugs in regular JavaScript programs? And if not, are there any reasons why your tool performs better than existing tools that focus on regular JavaScript programs?
Okay, good question. WeChat mini program bugs contains the regular JavaScript bugs because the because the program logic is written by JavaScript. Our tool does not perform better than some existing tools such as JetLint or something else. Our tool is based on the bug patterns we summarized from our empirical study. Therefore, if some tools you can apply our bug patterns on existing tools, they can also detect the known bugs. Yes.
Mm-hmm. All right. Thanks, Tao. I have a question. Sorry. Does somebody?
Go ahead.
Go ahead, Piming. No, you go ahead.
Oh, okay. Yeah, actually, I have a question for Action. I think you mentioned that you will basically generate partial libraries to kind of like make the analyze space smaller. You mentioned I remember you mentioned about downcasting arrow. I think that's a relatively simple type of bug to detect. If you want to detect like per se like more complicated type of bugs like data races, those kind of things, how can you easily generate like a summary for the library? Because it's not like a statement you can easily find, oh, there's a typecasting or so. You may need some more analysis to generate those kind of partial library summaries. How can you, I mean, apart from that, any more complicated bug does your tool support, something like that?
Right, that's a good question. And I don't know too much about data race analysis, but I can give you examples of some other analyses. So if you want to run a null pointer analysis, your queries are going to be all the method calls and field accesses in the program. If you want to run a taint analysis, your analysis queries will be all the sinks in the application code. If you want to run like a type state analysis, then the queries will be all the instructions that can possibly modify the state of the program.
Okay. Yeah. So basically, you need a single criteria to determine to find out those statements, right?
Yes. And
okay,
that is correct.
Yeah. Okay. Sounds good.
All right. I might actually just piggyback on that question here to you, actually, and say, well, let me first of all say that I'm really happy to see somebody who developed a tool that beats Averroes at precision, because the precision of Averroes is not that good in many more recent practical scenarios. So I'm really happy to see that as well. I just have a couple of questions there, if you don't mind. One of them is, in many of your slides, you mentioned something about Averroes that says that the recall is 100% theoretically. So what do you mean by theoretically?
Right. So there's a couple of reasons that the recall may not be 100% in practice. So one is, of course, there could be dynamic features, and even though Averroes does provide support for dynamic features, it can never guarantee that it'll cover 100% of the cases. And the second is that there are, again, some implementation issues because of which it may not get to a perfect 100% recall at the moment. And the third thing is that, so the library summary, the summary created by Averroes contains enough information for some kinds of analyses, but not all of them. So let's say we want to create a partial library for a null pointer analysis where we catch null pointer errors from fields that are not initialized. So the Averroes summary doesn't have information about field initialization. So we may miss those kinds of errors too.
Right. Yeah, that's true. So in your case, like, what is do you have any guarantees for correctness or soundness of the analysis result that would be the output of an analysis using the partial library that you generate?
Right. So there's actually there's sort of two variants of our tool. So the first, so one of the variants is a user can specify how many queries, what percentage of queries they want covered. So for example, the user may specify that they want at least 80% or 90% of the application code queries to be covered. And we'll keep expanding the partial library until we reach that point. And
I see.
so
Okay.
that variant will give, and the number of queries covered is a proxy for the recall. And the second variant is where the user can specify what percentage of the library that they want to include. In this case, the user gets a guarantee on the analysis time, but they won't get a guarantee on the recall.
Okay. I see. Nice. Cool. Thank you. Let's see if I missed any questions in the chat or. Yep. Pei-Ming, you seem to have a question.
Yeah, I also have a question for Ryan. I just am curious about whether your, I mean, when you do the code removal, are your method conservative, which means your method guarantees that you will not remove something that user actually relies on. If it is conservative, how did you guarantee it? If it's not, do you think how do you think the programmer will react to the fact that you made?
Yeah, that's
you stole my question.
Crux of the problem. Oh, good. Get to it once then. So yeah, basically to answer your second half of that first, the way the programmer would react if you were a little overzealous with how much code you removed is probably upset because it have binary. Most likely, that's kind of around the side of conservatism, but I would assume it would be more likely to introduce bugs. Now, what ends up happening is because we have this differential code coverage analysis for features versus features disabled, if there's ever a case where, say, there's some utility functionality that is used by multiple features, then that code is still going to be highlighted for both for more runs. So it won't remove that code, even if it's kind of a feature agnostic bit of code. Sorry, even if it's related to a feature, it will be left behind because it's used by another feature. Does that make sense? So we only remove it if used by the feature that you're targeting for removal.
Yeah, that makes sense. But the problem is that you are using some. If I understand correctly, your method is based on some sort of dynamic analysis. So it's somehow in practice it's impossible to reach 100% code coverage as your experiment result also show. So it's still theoretically still not. Maybe practically you can maybe 99% of the time you can guarantee that you do not remove something, but something necessary.
So this
still possible, right?
So you're exactly right. Since it's a dynamic analysis approach, we can't guarantee that it's 100% coverage as going to get everything. But by not hitting 100%, you're not saying you are maybe mistakenly removing code that doesn't belong to this feature, but instead you're saying if I don't hit 100%, then some code that does pertain to that feature. which means that optimal amount of code in those cases, but we're also not breaking other features in those cases. So we go for soundness over completeness in this case.
Okay, I see. Okay.
Does that answer your question?
Yeah, thank you.
Sure.
So as a quick follow-up on that, actually, how with cases where code dependencies arise at runtime, so not necessarily during the building of the application or compiling the application into binaries, like I'm thinking about like in Java, for example, you might have something that is called through reflection or other weird ways. Like how do you deal with those, or do you just assume that the world doesn't contain these features for now?
That's a really good question that could result in some. We assume that that's not within scope. That's why we primarily target C languages like C, C++, and Rust.
But yeah, but C also has similar feature, right?
Dependencies. We don't actually. Sorry.
I mean, C also has similar feature. Like you can load a dynamic library and you use symbol lookup using some string to find the.
Sure. You can do that. We just don't actually handle those cases since our tool is set as a handful of like compiler passes to happen at compilation time. So if there's other dependencies at runtime, then that might the program might try to load one of the dependencies for the feature we removed, which should theoretically not break anything either, but that's kind of unnecessary overhead that we're incurring. So that's not ideal, but it's not breaking.
It again. I was just saying thank you. So I have a quick question to Pavle about your analysis. So in the way that you explained how notebooks are usually can execute, you can basically execute them in various different orders. You can execute 1, 4, 5, 1, 2, 4. Yeah. So in cases like that, like, do you find that it's harder to prove or guarantee analysis that is going to run on these notebooks because there's basically many different permutations of the ways that you're going to run the code, or does the abstract interpretation framework that you have help out with that as well?
Yeah, I mean, that's the whole point. That's the whole point of the PHI, right? So about 40 to 50%, there's even estimates that are larger, of notebooks have this out of order execution. They kind of like embed several programs into one kind of program, and if you do it the naive way, you get some really funky results, right? And so the idea of this PHI node really models the dependencies, and also obviously you'd have to reason about things that are unbound in a like next cell, and dead states, like unreachable states that your analysis can prove. But in principle, you can embed any analyzer into this framework, and we're kind of working on this. And as long as you kind of give us the PHI along with it, your analyzer will be able to run on notebook semantics.
Right. Okay, I see. Thank you. Again, let me see if there are any questions in the chat that I might have missed. I don't see any questions in the chat. I just have one more question for Pei-Ming. Do you? I don't know if you are aware of the work done by Kieran Zhang, Yuanbu Li, and Tom Reps about fast graph simplification for interdike reachability. It again works on the same idea of reducing the computation graph of a data flow analysis, trying to get better performance. If you are aware of that work, like, how does your work compare to theirs? And if you aren't, how does your work, generally speaking, compare to other work that is working on reducing those computation graphs for various other analysis abstractions?
Yeah, I actually know the work you are talking about, but if
Okay,
I
cool.
remember correctly, I think they're actually different. I think, of course, their method is also another way to approaching this problem, because they're using self-fail reachability, which is a kind of on-demand program analysis. Like you query and you do the graph reachability test on the on the constraint graph also. But what I'm presenting today is like a one-round analysis. I compute all the things and at once and generate all the result. And whenever user queries, I just return the result I already computed. So I think that definitely has some similarity between the idea, but when the in the implementation wise, they're totally different because they're different way to approach in this approach. Yeah, I hope that answers your question.
Yep. Thank you. Mike, I do have a question for you. So, how would we feedback some of the outcomes of your research and your work back into generating test cases for regular programs rather than chemical reaction networks? Sorry. Would any of the outcomes there be applicable to reasoning about, I don't know, I'm thinking about rules that govern like API usage or rules that govern data flow analyses and stuff like that? Or would any of these techniques be still applicable there? Can we draw any results from that?
Yeah, I think I see the largest kind of crossover from what we're learning from these chemical reaction networks is kind of in the flaky behavior. So these programs are inherently probabilistic in their output. So we've kind of had to handle how do you write test suites that handle that behavior and still give us results, because like the program's going to fail some percentage of the time because that's how the program is, but that still may be a passing case. And especially with some of the more complex models, when we start going and putting the multiple CRNs together to get the more complex outputs, then the functions start becoming probabilistic even in like our specification. So I think some of the techniques we're developing kind of handle when we can say the flakiness is valid versus, it's actually a true error. I think maybe some of that can be pulled out and kind of address the larger issue in the space of, rather than just saying a flaky test is bad, maybe we need to evaluate these flaky tests on other programs to kind of gain more insights.
Interesting. Yeah, I actually didn't think about it this way. That's quite an interesting insight. Yeah, sometimes like when I'm dealing with, for example, like JIT compilers, for example, like testing them is like, you never know like what the actual inliners, for example, at runtime, like what kind of decisions they're going to make, and sometimes the tests that we have are kind of flaky, quote unquote, in that sense, and it would be nice to evaluate them in a way like that. Yeah. Thank you. I appreciate it. I don't see any further questions in the chat. Anybody has any other questions to our speakers or speakers to anyone in the audience? Well, in that case, I'd like to thank you all again for your talks and for your time and effort and being here today. I really appreciate it. And I wish you all the best with the rest of the conference. Thank you, folks.
Thank you.
Thank you, everyone.
Bye-bye.
Bye-bye.
Bye-bye.